Okay, it's 5:25, so let's get started. Yeah.
Can you explain homomorphism a little bit?
I can, but I have announcements.
Okay.
So, exam 2's up here. Please pick them up. I don't want to keep carrying them around. Please pick them up. You know about the announcement, all that stuff. Any questions about midterm 2? Solutions are up, by the way. Yeah.
For the pumping limit,
Yeah.
how come we wouldn't use like 0 to the
2 times p?
Yeah.
Well,
Why is that?
is that a power of 2?
That wasn't the definition.
Yeah, a power of an integer. The length of w is a power of n. Yeah, it's n to some number, some integer. Just like 0 to the 2 to the n is just a powers of 2.
I just thought it was just the length of W was just power of the I didn't think it was 2 to the power of 2.
Well, power is still going to be even number to some number.
Right. I thought it meant all. I had to see power.
Yeah, it's going to include like 2 to the some number, 4 to some number, 6 to some number. Yeah. Yeah. Question? Other questions? Guys? Yeah.
So, yeah, the power is not even, right?
Yep.
So, I mean, why wouldn't 0, it has to have a 0 and a 1, or a 0 or
It could, but it doesn't have to.
or yeah.
As long as I pick some string in the language of length at least p.
Right. So
Mhm.
then, why is 0p 1p?
Well, that's not necessarily in the language because that has length 2p, which goes back to the point we just talked about.
If p is forcing e.
Well, that's just 2 times an even number, which is not necessarily a power of an even number.
There has to be power.
That's what the question says. Other questions about midterm 2?
Yeah, why not?
Yeah.
So for the first one, I don't know, I did a little proof thing. My comment was like, great, but could it be some other even
Yeah.
power? Like, how would
Yeah,
you
that's what I thought.
Yeah, so if you prove that it's not a power of 2, it could be a power of 4 or a
Yeah,
power
no,
of
like, I
6.
get it, but like, how would you go about that?
Solutions.
Oh, yeah.
The easiest proof is that it's not a power of 2, but what if it was some other power, say,
Are you doing it? Oh.
yeah, so let's just say it's n to the k where n is even, okay? So it's some power, it's a power of an even number. Well, we can just write that as 2m because n is even to the k. Well, this is
Oh, I see
just
where you're
2 to the
going.
k, m to the k. Well, if it isn't a power of 2, it can't be of this form either because there's an embedded power of 2.
Right.
And so therefore it's proven.
Cool.
Yep.
So with regard to that as well, I was watching some videos from some very nice Indian people who were doing it on YouTube, and they said that every time I watched someone different do it, they only disproved one case. They didn't do all of them because
Well, that's wrong then.
They said, well, their reasoning was, one case doesn't work, so therefore you don't have to go further because you already found one.
No, one case maybe, but every decomposition,
Yeah.
those are different things.
Okay.
Like, for instance, like 0 to the n, 1 to the n when we did the regular one, there was only one case that because the x and y can only be zeros.
Okay.
But there are many decompositions. Those are different
Okay.
things. Mhm.
There's some different vocabulary.
Yeah. Other questions? All right. P set 4 is still out. Any questions about P set 4?
I don't see if you answered my question yet.
I think I have. Any questions about P set 4? Okay, since the last Wednesday is the final exam, and obviously there's no reason for me to hold office hours, I'm going to hold extra office hours next Friday. So not just Monday and Wednesday, then the next Monday is going to be Monday, Wednesday, Friday, Monday for office hours. Yeah.
Speaking of final Are you going to do some kind of review for it? Is that just
Yes.
Okay.
Yeah, so I'm planning on the very last class to be the first half about my research, because I think that might be pretty interesting, and then the second half is final exam review, then the office hours also final exam review. Yeah.
Is the final exam just during regular class time?
Yeah, the entire last lecture time. Yep. I'll talk about it when it gets closer. Other questions? So I'm going to give you a really nice present. Okay?
Thank you.
If it, you don't even know what it is yet. So if there's a lot of questions on Piazza about problem sets 4 and 5 and active participation coming to the final exam review and everything, the final exam will only have information for the non-bonus problems ending today. So ignore the bonus problem on the final exam. Everything that could be tested ends today, at the end of today.
Are we serious?
Yep, I'm serious. If there's enough participation. And so the entire next week will be all really cool things that may appear as a bonus problem, but they're not on the non-bonus problems.
Wow, so that means that we need to make sure everyone's participating in Piazza?
Participating in Piazza, working hard on problem sets 4 and 5, and attending the final exam review.
Okay. Thank you.
And office hours, yeah.
How do we,
Ryan 2020.
how do we
Ryan 2020.
Okay?
Replace Crow.
But we have a lot to get through today. So are there any questions otherwise? Yeah.
So we've been covering a lot of simulating the machine.
Yep. Mm-hmm.
But my question is it seems like when you or Andrew solve these problems, it seems like you're just imagining
Yeah.
exactly what to
Yeah.
do.
Mhm.
But I'm not really sure like how we gain the intuition
Yeah.
to be able to solve these problems.
Yeah. So it depends on what problem you're talking about. Are you talking about proving a decidability or showing something's undecidable? So decidability. That's a little harder to answer because it depends on the problem you're talking about. Like in the case of eDFA, for testing emptiness of DFAs. Well, if you can reach a final state, then from the start state, then this language is certainly not empty. So you turn that into a graph problem. It's really just trying to analyze the structure of what the question's really asking. All DFA, for instance, is there any state you can reach that's not a final state? Then therefore the language is not everything. Or in the case of infinite DFA, the language is infinite if there's some loop from the start state you can get to some loop and that goes to a final state, right? Because I can repeat that as many times as I like. Well, that's just a pumping lemma again. And you just analyze the structure of how we actually got through the pumping lemma, and we only got there because there was some string in the language of length at least p, which is the number of states in DFA. So you just figure out, okay, it's in the language of the machine and has length at least p, so you make the machine and a DFA of length at least p, and it has to begin both of them, so you do intersection. And so then you just test, is it empty or not? Okay? It's really just analyzing the structure, yeah.
Okay, so now about Rice's theorem.
Yeah, we'll do that today.
If we are given a problem that tells us to decide whether a property of Turing machines is decidable, it says to prove it is.
Yeah.
Then can we just say, well, by Rice's theorem, it must be because you're actually telling us to show that it is decidable, so it must be.
We won't make a blunder like that, but it would have to be a trivial property in the case that either every Turing machine has that property or none do. So if I asked, does this? So there's a little difference here. Is it a property of the language of Turing machines or a property of Turing machines? Language. Then it would have to be trivial, because Rice's theorem says every non-trivial property is undecidable. Yeah. So it would be like every Turing machine. So the set of all Turing machines that accept at least 0 strings. Well, every Turing machine does that. Or all the Turing machines that accept -1 strings. Well, that's none of them. So those are decidable. But anything that's non-trivial, that's undecidable, as we'll see today. Yeah.
So for proving undecidability, now that we have a tool for Rice's theorem,
Well, I'll prove it today, but
okay.
yeah.
But
But
is that best practice to prove undecidability versus
You-
doing a high level one?
it's far easier to use Rice's theorem, but you can't apply it everywhere.
Okay.
Because like in the case of, say, EQTM, that takes 2 machines, whereas Rice's theorem only works with single Turing machine descriptions.
Okay.
Yeah, so you can't apply everywhere, but when you can, use it, because it's far easier. But, and also, like, even if you have single machine descriptions, and let's just say the machine's language is not empty and has at least 5 states, that is not a property of the language anymore.
Okay.
Because there's something about the description itself that actually makes a difference. It's only about the language here.
Okay.
Yeah. Other questions? Okay, so let's get back to Rice's theorem. So I copied and pasted what we talked about on Wednesday. We talked about these things called properties of Turing machine languages. And we said it was the set of all descriptions such that we wanted to have it only depend on the language whether you had the property or not. Or, in other words, you're in the language P or you're not in the language P. Okay? So we just define it to say, if you have equal language for any 2 Turing machines, either they both have the property or neither do. So like emptiness, for example, either you're both empty or both not empty, for sure. So that's a property of Turing machine languages. Non-trivial property is that there's some machine that doesn't have the property and some machine that does. So obviously a trivial one would mean every Turing machine has the property or none of them do. Okay? And what Rice's theorem says is that every non-trivial property is undecidable. Yeah.
So then trivial properties are things that we use to describe like not necessarily the mechanics, but things like the states and the transitions.
No.
Not yet.
I mean non-trivial property of Turing machine languages.
Okay.
There could still be undecidable properties that don't entirely have to do with language, like for example, the language is empty and has at least 5 states. That's undecidable, but it's not a property of the language.
I see.
Yeah.
So if you wanted to prove that something's undecidable and you wanted to use Rice's theorem, you have to actually show that one has one property that doesn't.
Yeah, you have to show 2 things. You have to show that it's a property of Turing machine languages, that if you have 2 arbitrary machines, either are both in the language or neither. So it's only dependent on the language whether you have the property or not. And then you have to show that it's non-trivial, which is what you said, that one of them has the property and one doesn't. Okay?
Wait, the first one you said, am I missing something? So they both have to be in the language, both don't.
No, so the first one is 2 arbitrary Turing machines. Arbitrary. So any 2 Turing machines, if they have the same language, they either are both in the language or neither are. The second one, you show 2 specific examples, one that has the property and one that doesn't. Okay? Other questions? Okay, so let's prove Rice's theorem. So this one's going to probably be the hardest proof in the class, but so just make sure you're paying attention to this one. Well, we haven't really proven Rice's theorem yet, so I can't say anything about this property being undecidable. So what method do we have to show that something is undecidable so far?
Deciders.
Not deciders. Using a reduction, right. So if we assume that this property is decidable, and I can show that using that decider, I can decide something that is already undecidable, then there's no way that this thing could be decidable. right? Because if it were, then I can decide this undecidable problem, which certainly can happen. Oh, yeah.
Say that one more time.
Yeah, sure. Let me just write this. So let P be an arbitrary, non-trivial property of TM languages. And then we're going to show that P is undecidable. So what do we want here? The method that we have so far to prove something is undecidable is if we assume that it's decidable, then we can decide something that is undecidable, or we proved undecidable already. Like, for example, we proved that EQTM is undecidable because we assume that there's a decider for it, and then using that decider, we were able to decide ETM, emptiness, for Turing machines. But we already know that that's undecidable from before. And so therefore, there's no way that EQTM could have been decidable. Okay? Does that make sense? It's just a proof by contradiction. So it's essentially saying ETM undecidable implies EQTM undecidable, contrapositive. EQTM decidable implies ETM decidable. It's just a contrapositive. Yeah. Other questions? Okay. So if I want to show that P is undecidable, the way that we know so far is to suppose it is decidable, then solve some undecidable problem. So let's suppose that P is decidable. Well, now I got to pick which problem I want to show using this supposition now is decidable. So we have a couple of choices. We have ATM, ETM, EQTM, a lot of different possibilities we can choose. But I think the one that we started from was ATM. So why not just start with that one? So we will try to decide ATM as follows. So now, what does a supposed decider for ATM take as input? A machine and a string. Good. So on input, MW, and then now I got to use P in some important way here. So let's think back to how we did the proofs for, let's say, ETM being undecidable. Well, what we did is we supposed it's decidable, and then we used that decider on a machine that we constructed that had two different behaviors. It had one behavior if M accepts W, and another behavior if M does not accept W. Okay? So that kind of idea is, so I should say, those two different behaviors, when I make a machine for it, can be decided by this supposed decider. And by doing that, now I can determine which of those two possibilities happened. And so I can determine whether M accepts W or not. So that's just how we did it to show that ETM is undecidable. In fact, that's how we're going to do the exact same thing here. We're going to make a machine that has two different behaviors. One particular behavior if M accepts W, and another behavior if M happens to not accept W. Okay? Any questions so far? Yeah.
So are we going to bring this back to how then this gives us a non-trivial property?
Yes.
Okay.
Yeah. We're actually going to do that right now. Okay? Well, what we did before is that to get those two different behaviors, we started off accepting some number of strings right at the very start. And then if M accepts W, then we accept more strings or change the language or do something non-trivial so that we get the other behavior. Same thing here. So what are we going to do? We're going to start off at empty language and then end up at something that acts differently. Well, let's see. Does a machine that has the empty language have property P? I don't know. It may. Well, let's suppose it does. So let's suppose, so I'm going to put it over here. Suppose that M is a TM that has empty language. And suppose M's description is in P. Or in other words, M has property P. Actually, I'm going to give it a name, sorry. M sub empty. Just to remind us that it has the empty language. Okay? Well, what if it didn't have property P? If I show P is undecidable, is P bar decidable? Or is it also undecidable? Well, it's complement. We showed that decidable languages are closed in complement. So P bar must also be undecidable. So whether this machine has property P or not, it doesn't matter. As long as it's one of them, then I can decide the other, or I can show how to prove the other undecidable just by flipping P and P bar. That's it. So I'm just making a supposition without loss of generality here. Yeah.
So if we prove that M is decidable, we can say that P is.
Be careful. A machine's not decidable. So if I show that the case of where M does have property P, and then eventually show P is an undecidable property, then it must also be that P bar is also an undecidable property. So it doesn't matter whether M sub empty is in P or P bar, as long as I pick one. Well, I know that there is such a machine. Why? How do I know there is a machine with property P? Well, what do I know about P? It's a non-trivial property. There's some machine with the property. Well, let's suppose that this is one of them. There may be more. Let's suppose that this is one. What else do I know about? Actually, no. I did this backwards. It should be, doesn't have property P, but it doesn't matter because I can just flip which one it is. Well, sorry about that. So I know that so I'm supposing that this machine doesn't have property P. Well, because P is a non-trivial property, what else do I know? Yeah, there's a machine that has the property also. Does it have empty language?
Yeah.
No, not M sub empty, the other one. Could it have empty language? It's a property of Turing Machine languages. If they have the same language, then they either both have the property or neither do. Okay? So, for any machine that does have property P using this supposition, it has non-empty language. So now suppose T is a TM and T has property P. Okay? So now we have the two behaviors we want. What we're going to do is, depending on whether M accepts W, yeah, go ahead.
So you said that if they have identical languages, then they should both have property
Mhm.
So if that works the other way too, they have property P, then they both have the same.
No, they don't necessarily. No. Yeah, because I may have all but the empty language Turing machines have the property and the empty ones don't. So just because you have the property doesn't mean they have the same language. But if you have the same language, then you either both have the property or neither do.
Oh.
The converse doesn't work the same way. Okay. Okay. Well, here are the two behaviors that we're going to have. Depending on whether M accepts W, I'm going to have the machine that I'm going to build inside this machine have language T, depending on whether M accepts W or not, and otherwise be like M sub empty. And then, because I know P is decidable, then I can differentiate which one of those two it is. And so, therefore, that'll tell me something about whether M accepts W or not. Okay? So, we're going to construct. So, by the way, this is a solved exercise in Chapter 5 if you don't get all of this at the first glance. So, let's construct Turing machine M prime. And this can take arbitrary input, let's call it X. So this, next bit may be the most important part of the proof. Once this machine starts up, when it's given this Turing machine M and this machine W, the outer machine I mean, once it's given those two things, is the fact of whether M accepts W fixed? If I run M on W, could it give a different answer if I ran it twice? No, it's fixed, okay? So we're going to use that right here. So if M does not accept W, we're going to have it behave like M sub empty. So what we're going to do is simulate M on W. If M rejects W, we're going to reject X. So I'll go over it. So the fact of whether M accepts W says accept or runs forever or whatever on input W is fixed. So that must mean if M rejects W, that fact, whether it's true or false, is fixed. So if M rejects W, I'm going to reject every X that this M prime could ever receive. So its language is, if that's true. It must be empty. If M really does reject W, this, so it'll reject every possible input. So its language is empty. So now we either ran forever on W or we accepted W, because those are the only two outcomes. What if we ran forever on W? Will I ever progress to the next step? No. So will I ever accept anything? No, so its language is empty. So now we need to worry about when it accepts. Okay? So if it accepts, we're not going to have this M prime thing behave like M sub empty. We're going to have it behave like T, the thing that does have property P. So run T on X and accept if T accepts. So after this, it gets a lot easier. But let's go over how this machine works. It says, let's handle the three cases of whether M accepts W or whatever on W. If M does accept W, well, we're ignoring the if M rejects W step. Then we're going to run T on X. And whatever t says, we're going to accept x in that case. So m prime is going to behave like t now, because m accepts w. Okay, so, which does have property p now. Yeah.
Could you explain why you thought of using them prime? What was the
Because we have a supposed decider for the property p, and so now it'll tell me which of those two properties it could have been, either like t or like empty.
So when would you have, like, why did you think of using that?
Because the property is a set of Turing machine descriptions, and we need to feed it a single machine and it'll tell me supposedly whether it has the property or doesn't, because it's a decider, supposedly. Okay? And the way we set this up is that it behaves like m empty, which doesn't have the property if m does not accept w, and it behaves like t, which has the property if it does. So by having this supposed decider tell me whether it has the property or not, tells me something about whether m accepts w or not. Okay? Yeah.
It's like kind of like intuitively know that you had to make this decider.
Yeah, I need to feed this supposed decider some machine. Yeah, I need to feed it some machine, and we wanted it to be like the reductions we've seen before, which is it behaves like one machine in one case where m accepts w, and like another machine in another case. And we wanted it so that one machine has the property and the other doesn't. Yeah.
So if he runs forever on X or rejects it?
It doesn't matter. It'll only accept the strings that it actually does accept. So its language is only the strings that it accepts. Mm-hmm. So it behaves exactly like how T would on any input. So I'll go over this once we finish it up. Well, once we make this machine, now we gotta feed it to this supposed decider for this property P. Well, let's call it D be the decider for this property P, and run D on description of, not T, sorry, M prime. And since D is a decider, could it run forever? No. So if D accepts, we got to do something, bake a cake. And if D rejects, we got to do something else. Well, let's see. If D accepts, what does that tell me about M prime? What must it have? It must have property P, because that's what the decider is supposed to do. Okay, so if it does have property P, how did M prime behave? It behaved like T, because we assumed that that had property P. Okay, well if M prime behaved like T, what was the answer of whether M accepted W or not? What could have been the answer? Could it have run forever or rejected? No, because if it rejected, we would have rejected X at the beginning, and it wouldn't have behaved like T. If it ran forever, then it wouldn't have accepted anything either. So what must have M done on input W? Accepted. So my supposed decider for ATM, what am I supposed to say to it? Accept. Yeah. So I say accept. And then now the other case. If D rejects, that must mean M prime does not have property P. All right? Well, what machine must have M prime imitated? M sub empty, or in other words, had empty language. Did M accept W or not? No, it couldn't have, because if it did, we would have behaved like T. But we behaved like the other machine. And so therefore, M did not accept W. So what should I say for my decider for ATM? Reject. So this is almost, so it's just, all it is just a generalization of the reductions we've already seen to allow for any non-trivial Turing machine language properties. Okay? So let's just recap. Since it's a non-trivial property, there must be some machine with the property and some machine without, by definition. And the empty language either has property P or doesn't. So we're just going to assume it doesn't, because I can just flip P and P bar, and the proof would work exactly the same. No differences other than that. So let's say that the empty language, any machine with the empty language, does not have property P. Well, there's some other machine that does have property P by definition, right? So we have this machine M prime that behaves like M empty or T, depending on what M did on W. So we behave like M empty if either M rejects W or happens to run forever on W, in which case I wouldn't progress to the next step anyway. So if M does not accept W, we behave like M empty, which doesn't have the property. Otherwise, we behave exactly like T would, which does have the property. And so therefore, if we assume that this property is decidable, then we can decide which one of those two outcomes it happened. And so therefore, we can figure out whether M accepts W or not. Yeah. Mm-hmm. Because it never accepts anything.
Yeah.
Yep.
But how would you know? Like I understand if you reject, and if you have the case where does reject W, you reject. But then if you're in a case where he rejects, how do you know it's not the case where it runs forever? And in which case, how would you know to reject because it would be running forever?
Well, if D rejects, that must mean M prime does not have the property.
Yeah.
Which means it must, because this M prime only has those two outcomes, it must have behaved like the M empty language, M empty Turing machine, sorry. Which the only way that that could happen is if M did not accept W. Because if M did accept W, then it behaves like T. But we said T doesn't have empty language. Because if it did, it wouldn't have had property P. Okay? Any questions? So I definitely wouldn't ask you to reproduce this, but it's important to understand what is happening behind the scenes here. All it is just a reduction from ATM. Yeah.
Wait, I thought was this supposed to be a proof of this?
Yeah, this is a proof of Rice's theorem. So it's there. Yeah. Yeah, it's a proof of Rice's theorem.
It's on page 243.
243, which is what I'm open to right now. But any questions about that? So let's prove one language undecidable, or one property undecidable, I guess. Now I got to think of an example. Okay. So I'll mimic one that's kind of like the one on the midterm you've seen. So the language, instead of 3 DFA, I'm asking about 3 Turing machine, which says all Turing machines that have at most 3 strings in their language. Okay? And I claim this is undecidable. Okay? is it possible for me to apply Rice's theorem in this situation?
Yes.
Yeah, so I can't immediately reject because it only deals with single Turing machine descriptions. So I can't just throw Rice's theorem out the door right now. I could apply Rice's theorem. Maybe I can't, but it's just a preliminary check. Well, in order for me to apply Rice's theorem, what two things do I need to show? Yeah, so it's a property of Turing machine languages, and also what? Non-trivial. So let's do the first one. So what did the property of Turing machine languages part say?
Where you would have, if you had two,
Mhm.
whatever languages, it's either a property of both or property of
Yes. So if I have two arbitrary Turing machines with the same language, it can't ever be the case that one of them has the property and the other one does not have the property. Okay? So if L of M1 equals L of M2, could it ever be the case that M1 has 2 strings in its language and M2 has 4 strings in its language? No, because they have the same language. Then either both have at most 3 strings or neither do. Kind of like Rice's theorem because the proof is really difficult, but applying it is super easy. So it's pretty cool. But does that make sense? Two arbitrary Turing machines with the same language, then either both of them are in 3TM or neither are. Okay? Well, we showed as a property of Turing machine languages. Now we got to show, fill in the blank, non-trivial. All right. So in order for me to show non-triviality of 3TM, what do we need to show? Exactly. I need to show one machine that has the property 3TM and another one that doesn't. What's one that does? Any example works. No, that does. Oh, yeah, I'm thinking backwards. Yeah, one that does have the property is any machine that happens to reject every single string. So let M1 be a TM that you can either say rejects everything or has empty language. Well, then, therefore, since its language has at most 3 strings, M1 must be in 3TM.
So this is a good strategy. Just pick something that you already know, you've already
Yeah.
proven.
Yeah.
So you define M1 and M2?
Like this is yeah. Yeah, it shouldn't be excessively complicated. Yeah. Okay. Any example of a Turing machine that doesn't have the property? Oh, sorry? Yeah, how about one that accepts everything? That has at least 3 strings. So, sorry, at least 4 strings. That's what I needed. Let M2 be a Turing machine that accepts everything. Then M2 is not in 3TM. Okay? So we showed that there's one machine that does have the property and another machine that doesn't. So what can I conclude? By Rice's theorem. Those are the 3 most important words of this proof, and probably the whole class. But by Rice's theorem, 3TM is undecidable. Yeah. Yeah, applying Rice's theorem is so much easier than doing a reduction, but you can't apply it everywhere, sadly. Yeah.
Does this, because of the whole, you have to show a proper Turing machine, does it only work with Turing machines?
Yes.
Yes.
And we're actually going to prove undecidability of context-free grammars in a bit, of some things about context-free grammars, and only applies to Turing machines here. Yep.
I have a question.
Yeah.
So for M1, you said that it rejects everything. If it rejects everything, then how can it have 3 strings?
It has at most 3 strings.
What if it rejects everything?
Yeah, it has 0 strings in its language.
Then it has 3 strings again?
It says at most 3 strings.
Oh, it doesn't say it has 3 strings.
It says right here, the language has at most 3 strings in it. Less than or equal to. Other questions?
Okay, this is kind of a stupid question.
Yeah.
Well, when I kind of read this, I kind of feel like the first statement is like to contradict, like the problem with the Turing machine is not trivial.
Mhm.
It's like either they both have to be equal or not.
Which part are you asking about?
The property of T and
Yeah.
So the languages have to be either equal or not.
Those are for 2 arbitrary Turing machines, yes.
So M1 and M2 that we defined below.
No, those are completely separate. Yeah, yeah. I should have named them something else, but the 2 parts are completely separate.
They're not.
Yeah, they're not connected at all. Yeah, yeah. Other questions? Okay, we have some more time, so let's continue. So, what have we done so far? A lot. But what things have we been talking about with respect to Turing machines? We've been talking about strings that Turing machines can accept. Then we can talk about encodings of Turing machines, in which case you take a Turing machine's encoding as input and then say something about that. Well, maybe what you can do is something like this. Suppose that you're running some Java program or whatever, and an exception gets thrown. What gets shown on the screen? A stack trace, right? A set of function calls that were taken at every single step, or a snapshot of the program at that given moment. Maybe we can talk about something related to that of Turing machines. Maybe we can think about all of the histories of computations that the Turing machine done as strings. So maybe what we can think about is, at the very start, you say what the starting configuration is, and then after one transition, here's the next configuration, then the next configuration, etc. Maybe we can talk about, if we string those together, delimited, maybe we can talk about the language of computation histories. And it actually turns out to be very useful in proving undecidability of some things. So, what we're going to define, a computation history of Turing machine M on W is a sequence of configurations, C0, C1, let's say CM is the last one. Well, this is just like when we talked about yields for the computations of Turing machines on inputs before. It actually turns out to be exactly the same here, where C0 is the start config. And for all values of I between 0 and m minus 1, ci yields ci plus 1. So just in other words, it's a valid computation of m on w, just written out. I think we defined this earlier, but the meaning of it, the name of it is called a computation history. Okay? And we say a computation history is accepting if CM is accepting, the last guy, and it's rejecting if it is, I drew it too much, if it is rejecting. Okay, so it's just the computation history is just a sequence of the configurations of the machine at every given moment, and each one yields the next one via a valid transition. And we say that it's an accepting computation history if the last guy has Q accept in there, and it's rejecting if it has Q reject in there. Okay? Any questions on definition? So we're going to be using computation histories throughout the rest of today. But I'm going to take a little bit of a detour and talk about a different model of computation. Everyone goes, yay! But so we talked about DFAs, we talked about context-free grammars and PDAs, and then we talked about Turing machines. And you may think, well, DFAs and context-free grammars, those are pretty low-level types of things, not very up the scale in terms of what you can compute. Then we go to Turing machines, which is way off the charts comparatively. And then you may say, well, if Turing machines are capable of the same thing as my computer, well, my computer has a fixed amount of memory. I can always add more if I wanted to, but I'm lazy and I don't keep adding memory to my computer, right? It has a fixed amount of memory. But I can do the same things as Turing machines in terms of going back and forth across the tape. Maybe we can talk about Turing machines that never go beyond their input, or some fixed length, let's say.
What do you mean go never beyond their
Yeah.
input?
So in this case, instead of a one-way infinite tape, we're going to have a fixed length tape where the tape's length is the length of the input, exactly. Okay? And so what these things are called are linear bounded automaton, or an LBA. Don't worry, there's no pumping lemma for LBAs or whatever. But using computation histories, we can actually just show that some problems about context-free grammars, for example, are undecidable, but we'll get there eventually. So is exactly like ATM, but can never move right past its input. I could talk about the, if you try to go right, then you bounce off the right-hand end of the tape in this case, but it actually won't matter in this part. Okay, so now I'm just guaranteeing you'll never move past the right-hand end of the tape. Okay? But it's deterministic single tape exactly the same, no differences, other than the tape being cut off at the end. Okay, any questions about LBAs? So maybe we can talk about, instead of ADFA, ACFG, which we proved decidable, then ATM, which we proved undecidable. Since this is could be less powerful than Turing machines because we limit the tape, we don't necessarily know whether this is decidable or not decidable. Okay? Well, it actually turns out, believe it or not, to be decidable. So let's talk about this problem. And then once we're done this, we'll take a break. So it's exactly the same as ATM. But it's an LBA in this case. And of course, if I try to move right past the end of the input, there's no like make a new tape cell or anything operation. The tape is fixed in size. So I claim that this is actually decidable. So this is right on the borderline between what is decidable and what isn't. If we limit the tape size, we can actually get decidability. So that actually proves that there are some Turing machines that need more space than what's given on the input. Because if they don't, then this is essentially the same as ATM, but this is decidable. Well, let's see. The tape size is fixed. So suppose input has n characters. In other words, there are n tape cells, which is a finite amount. Well, let's see. Suppose we had a configuration of the machine at one point. And then let's say I run it a little bit longer, and I get exactly the same tape contents, same state, and same tape head position. What must happen? A loop. And will I run forever? Why? Because these machines are deterministic. If I repeat a configuration with the same state in the same tape head location, I will run forever. Okay? Same with normal Turing machines. Same thing here. But can we detect an infinite loop in this case? Well, let's see. How many possible configurations are there? Well, suppose there are Q states and G tape symbols for concreteness. Well, let's see. How many possible, ignore the state and tape head location for a second. How many tape contents are there among those n cells? Well, how many choices do I have for the first cell? G. Second one? G, G, G. How many is that for n cells? N times G? Much larger. G to the n. That's the number of possible tape contents. So there are G to the n possible tape contents. Well, suppose that I went back to the exact same tape contents as I had before, but I was in a different state now. Can I guarantee I ran into a loop? No. So for each one of those possibilities of tape contents, how many states could I be in? It's just Q. It's just Q, right? For each one of those states, maybe I'm in a different tape head location than I was. How many tape head locations are there? N. Well, think about this for a second. If I look at G to the n times Q times n, That's the number of possible tape contents coupled together with all the possible states, coupled together with all the possible locations I could have been in. What if I ran for that amount of time, a number of transitions, plus 1? I must have repeated a configuration. Must, right? One of them must have happened because by the pigeonhole principle, there are only this many possible configurations with states and tape head location. But if I add one more and I still haven't accepted yet, I will repeat a configuration. So this is actually decidable. So how do we prove it? So on input MW, where M is an LBA. Run M on W for G to the N Q N plus 1 transitions, or until M stops, because it certainly could stop before then. If M has not accepted W by now, it's in a loop, so therefore we can reject. Has not, not accepted W, halted on W. Because it could very well reject beforehand. So just like we've done in a number of other settings, we just try all possibilities. Well, we know how many possibilities given an input Turing machine and its input string. Well, if it doesn't stop within that amount of time, it must repeat a configuration so we can detect an infinite loop. Well, then we just output what M said. Okay, so in the second step, we detect the case that it does run into an infinite loop. And then in the third step, that it must have stopped before then, so we just output whatever it said. So if it accepted W, then we say accept, otherwise we reject. And so now we can actually detect if this LBA can accept this input W. Because we can detect an infinite loop. And ATM is undecidable because we can't detect all possibilities of infinite loops. We can detect some clearly by here, but we can't detect them all. Yeah?
Could you repeat the significance of the Q and QN?
Yeah, because if we repeat the same contents of the tape, same state, and same tape head location, if we repeat that, then since these machines are deterministic, I will go back and do that loop over and over again.
But why G to the N, QN?
Because if there are G tape cells, then there can be G cells in the first cell, G symbols in the first cell, G symbols in the second cell, and all the way through the N cells. That's G times G to the N possibilities. Well, I can be in any one of those states. Well, if there are Q states, that must mean Q possibilities for each of those. And the tape head could be in any one of the N locations. So times N.
So that's like the possible.
Yeah,
Many possible.
that's the total number of possibilities. But if I add one more onto that, and I haven't accepted, then I will repeat it. Mm-hmm. Other questions? Okay, so I think it's good for a break. Then we'll prove that some other problems are undecidable.